Good morning, good afternoon, good evening, everybody, wherever you might be. It is my great pleasure to welcome our today's speaker, Paul Baum, my friend and colleague and my mentor, in fact. And this time I will give you a very juicy introduction, if you don't mind. Recently, we published a volume of the Banach Center publications in honor of Paul's birthday. It was 85th, right? Or 80, I forgot, 80th, sorry.
It was 80.
80, yes. And so I'll now start sharing the screen. And you should see the picture. Sorry, this is the wrong file. Maybe I'll skip the picture because anyway, you see Paul, right? So that's okay, but mouse is gone and it's difficult for me to manipulate without the mouse. Okay. So in this volume published last year in honor of Paul, by the Banach Center publications, Nigel and I, Nigel Hickson is Paul's colleague at Penn State University. We wrote some things about Paul, so I decided, to cop out, to do it the easy way, and instead of preparing a new introduction, I will just share with you what I find to be the most important in what Nigel and I wrote about Paul about a year ago. So don't worry, I'll not read everything, just the most important excerpts. So Paul began his career as an algebraic topologist. From the vantage point of his 1963 PhD thesis, it would have been very difficult to predict everything, or perhaps even anything, that followed in Paul's career. The work with Bott on singular foliations, the work with Fulton and McPherson on the Riemann-Roch theorem, and then the pioneering collaborations in non-commutative geometry with Douglas on the index theorem and K-homology. So this is what Alan Kohn was referring to yesterday, if you remember. And of course, with Kohn on the isomorphism conjecture, the famous Baum-Kohn conjecture. But the view looking backwards through time is of a purposeful journey from a landscape of apparently simple ideal mathematical objects, such as compact homogeneous spaces, to progressively wilder regions where the usual mathematical approaches become less and less effective and ever newer skills are demanded. Paul's trademark approach to mathematics has suited him well during his travels. Wherever he has found himself, he has asked the simplest questions about the simplest objects, and he has never been satisfied with anything but the simplest, most complete, most conceptual, and most revealing answers. Those answers have always led him towards a deep understanding of far more than the simple issues with which he began. The Baum-Kohn conjecture perfectly exemplifies Paul's approach, and even if the conjecture turns out to be wrong, there is no doubt that the question that Paul and Alain asked was right. The conjecture was based on the simplest of examples, initially the foliations of tori by lines of rational shape. Again, this is what Alain was showing to you yesterday. And the determined efforts of Paul and Alain to understand these examples in as fundamental a way as possible. The conjecture that emerged was truly audacious in scope, and in the early days, it might even have been called reckless. Paul, remind me, your original paper with Alain stating the conjecture was published like 16 years after you formulated it, right?
Well, we first published in formal notes, and that was done very quickly. That was done around 1980, and that dealt with some special cases, that is foliations and Lie groups. In fact, these notes were called, today we would say preprint. It was a preprint.
Yep.
But we didn't actually publish a formal mathematical paper for some time. Yeah, that took some years because we were struggling to get the conjecture into good shape.
Yep.
But we published, as I said a moment ago, we published these, we would say a preprint. We did that very quickly, right away, right after the Kingston meeting, which was in 1980.
Yeah, which again, Alain was telling you about yesterday. Okay, so let me continue, but it has withstood nearly 40 years of scrutiny, and there is no doubt that it points to a remarkable new duality between geometry and unitary representation theory that even now we only dimly comprehend. There is plenty to do during the next 40 years. That's for you, young guys. You know, the youngest people are on the second year undergraduate. So you have to be easy in your talk. Okay, meanwhile, Paul has ventured further and developed still more wonderful mathematics in the realm of quantum groups with his friends at IMPAN, in the smooth representation theory of p-adic groups with a steadily growing band of fellow travelers, and in other places too. He is forever in motion. Where will he travel next? So that's from Nigel Hickson. And I will start from here. So Paul's fundamental achievements in mathematics require no comment. We hold them as self-evident. So let me simply focus on the specific way he plays the game of theorems. His research is always curiosity-driven. He has never stopped being a child, craving to know what there is behind a closed door. Paul, do you remember once at the IMPAN, you climbed the table and opened the door, which was close to the ceiling? Do you remember this? It's really happened. You know, we have a crazy room at IMPAN with the walls, which are like 5 meters high. And right next to the ceiling, at the height of 3 meters above the floor, there is a door. So of course, Paul couldn't help it. He climbed the table and opened the door to find some cleaning equipment. But that's how you should be curious about mathematics. Okay, so where was it? Let me continue. His reasoning is crystal clear. He's never satisfied till he achieves the deepest understanding in the simplest possible terms. Once I invited him to work with me on a K-theory problem that was dormant for about 15 years because the torsion part cannot be detected by the index pairing. Together, we solved this problem within 50 days. Paul simply stared at the blackboard, repeating clearly true statements over and over again, each time slightly modifying them. To my astonishment, the initial unimpressive statement evolved into an idea solving the problem. The problem was dissolved by the lucidity of Paul's thinking, by his persistent probing of its nature. And now let me skip to the next page. To end with, let me say that a famous quote from John Templeton says, "It is nice to be important, but it's more important to be nice." Paul is a prime example of someone important who is also more than nice. We have a natural tendency to hang around people who influence us to become better persons, who not only are great themselves, but also capable and willing to share their greatness around. After being soaked for about 2 decades in Paul's way of doing mathematics, after having him as a role model, shaping my mathematical life to the great extent comparable only with the influence of my wonderful PhD supervisor, Mark Riffel, I can happily say that I'm truly proud of being Polish. Okay, so this was an introduction, a bit lengthy, but I couldn't resist it. You know, like with Oscar Wilde saying, I can resist everything except for temptations. So let me now quit this screen. I just must be careful not to quit Zoom. But yeah, but now I can show the picture. This is a picture which was chosen by Paul's wife for this volume. And I think this is a very good picture. So I encourage you to get this 120th volume of the Banach Center publications, and it's dedicated to Paul's on the occasion of his birthday. Okay, so I think we are done with the introduction. Now we can begin with mathematics. And this time, because, you know, Paul, yesterday Alain gave a brilliant lecture, but it was very difficult for people who don't know non-cumulative geometry. So I don't want you to be scared today. This lecture was given, for instance, in Colorado to third-year undergraduates, and I understood everything. So you can try to focus and really follow absolutely every line. And if you are stuck at any point, please don't hesitate to ask a question, just use a mic, okay? All right, Paul, so why don't you start sharing now? I will stop sharing.
I'm going to click on share screen.
Yes, please.
Okay. I clicked on share screen.
So while Paul is clicking on share screen, let me mention that all the talks are already on what happened thus far, already on our Banach Center YouTube channel, including Alain's yesterday talk. And I strongly encourage you to subscribe to the Banach Center YouTube channel.
Is it coming up? What do you say?
I don't see, still see you. I need to see the screen.
Yes.
They still didn't, yeah, something is coming, but no, that's not what I want.
All right, Adobe Reader. Should I click on that? Share. Share here. Okay, Adobe Reader. Now I'm clicking on share.
Yes, we've got it. We've got it.
Got it. Great.
Yeah.
Okay. Yeah.
So without any further ado, Paul, Frank Baum, what is K-theory and what is it good for? Paul, the floor is yours. The Zoom is yours. Take it away.
Oh, okay. Thank you, Piotr. All right, wonderful. So you said this would be a juicy introduction, and thank you for such a juicy introduction. Well,
what was it wrong, Gideon?
Oh no, it's wonderful, juicy. It's a very juicy, you know, like a big grapefruit. It's full of juice, you know. Yeah. Okay. So I intend this as an expository lecture. I'm just trying to do some exposition here. And as Piotr just said a moment ago, questions are welcome. Okay. So questions are welcome. Now, and it's always great to be back. With you in Poland. I have visited Penn many times, but I have also visited some other universities in Poland, and I'm very happy to be back with you once again. So, Dzień dobry. Okay, let's go. Oh, how do I advance this? I have to advance. Good. Yeah. All right, so in this talk, I shall try to make 4 points. First, the basic definition of K-theory. Now, I hope to convince you that that definition is in fact very simple and anybody can understand it. And then a brief history. K-theory is, I mean, as mathematics goes, K-theory is fairly new, somewhat new. So we can actually give a history of the subject. And then we shall compare algebraic to topological K-theory, and finally the unity of K-theory. And I dedicate this talk to the memory of Sir Michael Atiyah, who was a pioneer in this subject. Now, so suppose we have an abelian semigroup. So this is a set, J, with an addition, you know, A plus B, which is associative and commutative. Now, when you have an abelian group, there's a little trick. The French, Alain, for example, the French would say, un petit astuce, right? A little trick that converts the abelian semigroup to an abelian group. We call the abelian group J hat, J with a hat on top. What you do is you form the direct sum of the abelian semigroup with itself, and this is again an abelian semigroup, except now there are pairs. And then you introduce an equivalence relation, and this is the equivalence relation, that a pair Xi eta is defined to be equivalent to a pair Xi prime eta prime, if and only if there exists theta in the original abelian semigroup J with Xi plus eta prime plus theta equal to Xi prime plus eta plus theta. So this is an equivalence relation. And when you impose this equivalence relation on the direct sum J plus J, you have an abelian group, because now you can verify very easily that the inverse, the additive inverse of a pair Xi eta is the pair gotten by reversing the two. It's eta Xi. So for example, if you take the natural numbers, the positive integers, 1, 2, 3, so on, and this is an abelian semigroup. The addition is usual addition, right? 3 plus 5 equals 8, so on. Usual addition of the natural numbers. If you do this construction, you get Z. You get the integers, where now you will have both positive and negative integers. So that's an example of this. Now, let's look at the example we shall be interested in. Suppose we have a ring lambda with a unit 1 sub lambda. So that's a unit, multiplicative unit, 1 sub lambda. Then if we have some positive integer n, we can form the ring of all the n by n matrices, and this is with addition and matrix multiplication, as is usually the case. And this is again a ring with unit. The unit is now what you might call the identity matrix, the matrix that has 1 sub lambda down the diagonal and 0 every place else. So Mn of lambda is then again a ring with unit. Okay, now, so we fix, let's say, some positive integer n, and we can form GL n lambda, the invertible elements in the n by n matrices, Mn of lambda. So that will be the invertible elements. And now Pn of lambda, these are the idempotent matrices of n by n, of size n by n. So idempotent means alpha squared equal alpha, where it's matrix multiplication. You multiply by matrix multiplication, and if you have alpha squared equals alpha, then this is an idempotent matrix. And now we say that now we do a step which is just like ordinary linear algebra. We say that 2 n by n idempotent matrices, so we have alpha beta in P sub n of lambda, we say they are similar if there exists gamma, an invertible matrix, with gamma alpha gamma inverse equal beta. So we call that similarity. Now we let P of lambda, we let this be the set theoretic union of all the idempotent matrices of all different sizes. And we impose an equivalence relation, stable similarity, on P of lambda. So we have similarity, but now we shall impose an equivalence relation on the collection of all the idempotent matrices, which we shall call stable similarity. So what does stable similarity mean? Well, here is some notation. If R is a non-negative integer, then 0R, 0 sub R, this will be the R by R 0 matrix. Now we say that 2 idempotent matrices, alpha in P sub n of lambda, beta in P sub m of lambda, we shall say they are stably similar if and only if there exist non-negative integers Rs, with n plus R equals n plus S, and with alpha, we enlarge alpha by zeros. We take the direct sum of alpha with the 0 matrix, and then beta with the 0 matrix. If these two are similar, then we say that alpha and beta are stably similar. Now, if we do this, we take all the idempotent matrices and we put on that the equivalence relation of stable similarity. This is now an abelian semigroup. The addition is indicated here. The addition is direct sum of matrices where you put alpha here, beta here. This is the addition in this abelian semigroup. If you have 2 idempotent matrices and you do this, you again have an idempotent matrix. Now, it might not look abelian, but we had put this equivalence relation. In fact, this alpha beta is similar. It's similar to beta alpha, where you use the permutation matrix, the matrix that switches the first few indices with the last few indices. That gives the similarity. And so this is, in fact, an abelian semigroup. Okay, even though, as I say, it might not look abelian perhaps, but it's abelian. So now, this is just going over the definition of stably similar. So alpha and beta are stably similar if, when you enlarge by zeros, they become similar. That's stable similarity. Okay, so we started with a ring with unit. We use the idempotent matrices to make an abelian semigroup. And then we do the little trick, a petite astuce, which converts the abelian semigroup to a group, to an abelian group. We call this K naught of lambda, of the original ring with unit lambda. This is the basic definition of K theory. This is the definition, the basic definition. Any question about this? So by this construction, we associate to any ring with unit an abelian group. So that's the basic definition of K theory. Now, if we have two rings with unit and we have a ring homomorphism, which takes unit to unit, then we get a map of abelian groups from K naught lambda to K naught omega. And that, if we have an idempotent matrix, we just apply the phi to each entry in the matrix. This gives us an idempotent matrix over here for omega. And then we get a homomorphism of abelian groups. So in other words, this construction is functorial. This is a functorial construction. Now, if we have a field, any field, it could be a finite field, it could be the complex numbers, it could be a p-adic field, any field whatsoever. It is a theorem about idempotent matrices in a field, over a field. So if lambda is a field, it's a theorem, basically a linear algebra theorem, that two matrices, two idempotent matrices, are stably similar if and only if they have the same rank. It's if and only if they have the same rank. Well, what is the rank? Rank means that you take an n by n matrix and you take the rows, or if you prefer, you could take the columns. It doesn't matter. The row rank and the column rank is the same. But let's say we take the rows of the matrix. This spans a subvector space of lambda added to itself n times. And the dimension of that vector space spanned by the rows of the matrix is the rank of the matrix. So if you are working over a field, if lambda is a field, any field, then the abelian semigroup, it just depends on the rank. So the abelian semigroup is the non-negative integers. It's just a matter of the rank of the idempotent matrix. And then you do the little trick, you get an abelian group and you get Z. You get the integer Z. So K naught of a field is Z. Well, what happens if we don't have a field? So suppose we have a compact Hausdorff topological space, right? Compact Hausdorff topological space. Let's look at all the continuous complex valued functions. So all the continuous functions from the complex numbers, all the continuous functions from X, from this compact Hausdorff topological space to the complex numbers. Now this is C of X is a ring with unit. Of course, I know many people here are used to thinking of it as a C-star algebra, but it is, of course, a C-star algebra, but I'm just thinking of it for the moment as a ring with unit. And the operations, the ring operations, are what you might call the naive pointwise operations. So alpha plus beta, what does that mean? Evaluated at some point little x in capital X. So alpha plus beta evaluated at little x is alpha of x plus beta of x. And the multiplication, alpha beta, evaluated at some point x, is the product in the complex numbers, usual product in complex numbers, of alpha of x times beta of x. And the unit in this ring with unit, the unit is the constant function 1. And then we have the famous definition of Atiyah and Hirzebruch. If X is a compact Hausdorff topological space, they defined K upper naught of X to be this, that you take C of X and you take K naught C of X. Now, you may perhaps have heard this defined in terms of vector bundles. Any vector bundle on a compact Hausdorff space is in fact given by an idempotent matrix of continuous complex valued functions. And so this, what we are talking about here, the construction, converting the Abelian semigroup to an Abelian group using idempotent matrices, it gives exactly the same thing as if you did it with vector bundles. So this is the famous definition of Atiyah and Hirzebruch. They were very much inspired by what Grothendieck had done in algebraic geometry. Okay. Now, here is a very famous example. So we take the two sphere, the unit sphere in R3. So it's triples of real numbers, T1, T2, T3. The sum of the squares is 1. So this is the usual two sphere in R3. And then we have the coordinate functions. Xj, j equals 1, 2, 3. So xj of T1, T2, T3 is Tj. Now, this is the first really interesting example for K-theory. Of course, the continuous functions on S2 is certainly not a field. And for K naught, you get Z plus Z. Now, one of these Z's is just given by the 1-by-1 matrix consisting of the constant function 1. In other words, the unit of the ring. The other one is interesting. The other one is the generator for the other Z. This is the famous Hopf line bundle. If you look at it in terms of vector bundles, this is the famous line bundle of Heinz Hopf. Here is the matrix for that. It's this matrix where we are using the coordinate functions. It's an amusing exercise to actually verify that if by matrix multiplication, if you multiply this by itself, you get itself. In other words, this is an idempotent matrix. So I hope this illustrates the point I was trying to make just a moment ago, that any vector bundle is in fact given by, on a compact Hausdorff space, is given by an idempotent matrix. This is an example of that. Any questions about this, this example? So this is the first really interesting example for K-theory. Now, here's a brief history of K-theory. Well, Alexander Grothendieck, inspired by the Riemann-Roch theorem of Hirzebruch, which goes back to the classical work of Riemann and Roch. Roch was a very talented, very brilliant young mathematician, but alas, he died quite young. But Riemann and Roch, this was Riemann's last great achievement as a mathematician, the Riemann-Roch theorem, which he worked on it with Roch. Roch was what we would today call a postdoc. He had Riemann for his postdoc mentor. I mean, today we would say postdoc. And they did this wonderful thing known as the Riemann-Roch theorem. But then this was about what we would today call Riemann surfaces. In other words, algebraic varieties of complex dimension 1. So today we would call that a Riemann surface. But then for a century, mathematicians didn't know exactly what to, there were some results, but in higher dimensions, there were in fact some results. But people didn't really know what to do in higher dimensions, except that there were, as I say, there were some results. But then finally, it was understood what the problem was in higher dimensions. And very quickly, as soon as it was understood what the problem was, Grothendieck solved the problem. And that's the Grothendieck-Riemann-Roch theorem. Now, however, I'm sorry, that's the Hirzebruch-Riemann-Roch theorem. Hirzebruch solved the problem, and this was the Hirzebruch-Riemann-Roch theorem. Now, Grothendieck was not happy with Hirzebruch's proof. Grothendieck wanted to have a very kind of functorial, sort of conceptual proof. Hirzebruch had given a proof, but Grothendieck wanted a very functorial, very conceptual proof in what you might perhaps call the Grothendieck style. And he did that. He achieved that. And that was the birth of K-theory. He introduced K-theory in order to give a conceptual, functorial proof of the Hirzebruch theorem, of the Hirzebruch-Riemann-Roch theorem. However, it was not sufficiently general for Grothendieck's taste, so he never wrote it up. But Borel and Serre wrote it up. Borel and Serre wrote up Grothendieck's proof of the Grothendieck-Riemann-Roch theorem. Borel and Serre wrote it up, and it was published. And so this became the Grothendieck-Riemann-Roch theorem. Now, Atiyah and Hertz, and this was the birth of K-theory. So this happened within algebraic geometry. And of course, this was, these were wonderful developments. Those were the days, At my age, you are allowed to say that. You're allowed to say, well, those were the days. Okay, now, Atiyah and Hirzebruch attended many sort of in-person tutorials from Grothendieck, where Grothendieck explained to them his proof of the Hirzebruch theorem and the use that his marvelous and astounding proof makes of K-theory. Of course, this was all within algebraic geometry. But then Atiyah and Hirzebruch moved K-theory from algebraic geometry to topology. And this was a paper by Atiyah and Hirzebruch. They introduced in topology K-theory. And I gave just a moment ago the basic definition that they made, and within topology. And then there was a problem, which I'll try to outline for you the problem of vector fields on spheres. As soon as Atiyah and Hirzebruch introduced K-theory into topology, the race was on to use this new idea, K-theory, to solve the vector fields on spheres problem. The race was on, and many mathematicians were trying to do this. However, the race was won by Adams, J. Frank Adams. He used K-theory in topology to solve, I will try to explain all this in just a moment. He used K-theory to solve the problem of vector fields on spheres. Then the subject continued to evolve. We have K-theory for C-star algebras. Here we have Alain Kahn. And here you get involved in non-commutative ideas and groups, quantum groups. You have many workers, such as Professor Voronovich, who is here today. When you begin to think about what is really involved in Lie groups, and of course it leads you to quantum groups. And then you have K-theory for C-star algebras. So this was an important part of the development of K-theory. But we had another development, which was algebraic K-theory. And J.H.C. Whitehead was important in this, Bass, Hyman Bass, Daniel Quillen, and many mathematicians developed, Steve Lichtenbaum, many mathematicians developed what is called algebraic K-theory. So it appeared that the subject had split into two rather different parts, but there is, however, an underlying unity, which I shall try to explain. Now, what is the Hirzebruch-Riemann-Roch theorem? So we have a non-singular projective variety over the complex numbers, M. In other words, we write down a few polynomials, or homogeneous polynomials of some fixed fixed number of variables. They are homogeneous, can be of different degrees. We take the locus determined by that in CPM. So this is, and we assume that there are no singularities. So we have a non-singular projective algebraic variety. Now we have an algebraic vector bundle. So this is a vector bundle, but all structures are algebraic, not just continuous, but algebraic. So we can form the sheaf of germs of algebraic sections. This is now a sheaf on the algebraic variety, and then we can take the jth cohomology. We can take the cohomology using this sheaf. Now it's then, we have some lemmas here, which is that first of all, the dimension of each of these cohomology groups using the sheaf of germs of algebraic sections of the given vector bundle, those dimensions are finite and they vanish over the dimension, the complex dimension of the non-singular variety. Then we define the Riemann-Roch number. It's a kind of an Euler number. You take the alternating sum of the dimensions of these cohomology groups, and then we have this amazing formula of Hirzebruch. Here it is. This alternating sum of these dimensions, you take the Chern character, so this is a definite fixed polynomial in the Chern classes. You take the Chern character of E, you couple this with the Todd class of M. This is a definite fixed polynomial, the Todd polynomial, the Chern classes of M. You couple these two together using the usual cup product of algebraic topology, and then you evaluate on the fundamental cycle of M. This is an amazing thing because these individual dimensions, this is a topological answer. This is topology. If you were an algebraic topologist, you would say, well, of course. However, this is amazing. The point I'm trying to make, the point I'm attempting to make is that this is absolutely astounding because this is just topology. The right-hand side. It's just topology. That's all it is. Hirzebruch had to invent the Chern character and had to make precise what the Todd class is. He did all that. And he got this answer, this topological answer. The reason this is remarkable, I think, is that these individual dimensions are not topological. You cannot give a topological formula for these individual dimensions because they are not topological. In other words, we have what are called moduli. That is, on the same underlying C infinity vector bundle, you can have different algebraic structures as an algebraic vector bundle can be different. And if you keep the underlying topological vector bundle the same, but vary the moduli, vary the algebraic structure, these change, these individual dimensions change, but the alternating sum does not change. I mean, topologists know that these kind of Euler number kind of things tend to be very stable. And this is in fact what happens here. And then Hirzebruch gives his answer, his topological formula for this. And this is the Hirzebruch-Riemann-Roch theorem. If you go back to what Riemann and Roch did on a Riemann surface, it is this. In other words, this is an exact generalization of what Riemann and Roch did on a Riemann surface. Any question about this? This is Hirzebruch, known to everybody as Fritz. I was in his office one day. He gave me a copy, a signed copy of his book, his great book about Riemann rock. And I said, "Thank you very much, Professor Hirzebruch." And he said, "Well, I don't want you to call me Professor Hirzebruch. I want you to call me Fritz, like everybody." I said, "I cannot call you Fritz." He said, "Why not?" I said, "Because I admire this Riemann rock theorem, this beautiful theorem you have proved. I admire it so much that I have to call you Professor Hirzebruch." So he didn't know how to answer that. He looked down at his desk. He looked very sad. And I said, okay, I will call you Fritz. And from then on, I call him Fritz. And you can see he's giving a talk. He's working over the field with 5 elements, and he's giving a talk about SL2 of that formula group. So
I don't know if you know, but Fritz, or Professor Hirzebruch, he was the chairman of a Banach Center committee. So when you like to have a conference like ours in the Banach Center, you would be interviewed by Professor Hirzebruch or Fritz, who would come to Warsaw to interview applicants.
Well, in fact, I was aware of this because you had told it to me. That's why I was aware.
Yeah. Okay.
And, but I want to say something about Fritz.
Yeah.
He was, of course, an absolutely wonderful mathematician, but he also, in one of the ways you have just said, he devoted great amounts of time and energy to helping, especially young mathematicians. And this was a wonderful thing that he devoted great amounts of time and energy and attention to helping young mathematicians. Okay, so this is Fritz Hirzebruch.
In a way, that's what you're doing right now.
Oh, well, I hope so. Oh, look at this. This is Alexander Grothendieck. Here we have, I think, Mumford. This, I think, is Abianca. And this is, oh, these are well-known mathematicians. This, you know where this is? This is in India. This is at the Tata Institute in India. Artin, this is Artin back here. Grothendieck only went to India once, I believe, and this was taken during his visit. And in fact, I was in India at the same institute. I was giving a talk. I put this slide up. And I said, well, here's Grothendieck, you know, somewhere in France, probably at IHS. And everybody screamed, no, this is right here in the Tata Institute. So there is Alexander Grothendieck. Okay. Oh, this is Michael Atiyah. In fact, Sir Michael Atiyah. Very, very sadly, Sir Michael Atiyah has died. But here he was, of course, very, very active and played a very important role in the K-theory. So this is Michael Atiyah, Sir Michael Atiyah. Okay. And I dedicate this lecture to his memory. Now, okay, so.
Paul, may I ask you,
Sure.
because this is right now exactly 3:45. So if it is a good moment for a break, we can take it. If you want to finish some point, just go ahead. But I promise to remind you.
I think this is a good moment because we've had the brief history of K-theory.
Exactly.
Atiyah and Hirzebruch moved K-theory from algebraic geometry, where Grothendieck had created K-theory, moved it from algebraic geometry to topology. And then the race was on to use K-theory to solve the problem of vector fields on spheres. So, right, we take a break, and then, yes, this is a very good point, because then we take a break and then we'll discuss this whole problem of the vector fields on spheres. Okay, perfect. Great, wonderful.
Perfect, good. So let's have let's reconvene, let's resume at 4 p.m. sharp.
Okay, wonderful.
Okay, so I pause recording and we have a coffee break. Go. Yes, go ahead.
All right, okay now?
Yeah, now it's okay.
Okay, so Atiyah and Hirzebruch moved K-theory from algebraic geometry to topology. They introduced K theory into topology. All right, so at that time, this is all the 1950s. I'm going a little bit into the 60s, the 1960s. So there was a problem in topology at that time, the problem of the tangent vector fields on spheres. So if we let Sn-1, let this be the unit sphere in Rn. So this is the usual unit sphere in Rn. So Sn-1.
I think you should share the screen.
Share the screen?
But I see the screen.
New share?
I see just the general
sharing?
view of the lecture room.
I don't understand because I see the screen.
Are we sharing?
We see the screen. Is anybody? Yeah, everybody sees the screen.
It says you are screen sharing.
Yeah. You are screen sharing. I see your screen. Well, we see your screen in the lecture room.
We can see the screen.
Yes.
You can
We see the screen. Yeah.
So I am sharing.
You are sharing. Yeah. Yes. You are good. You are good.
Something is wrong in my device, but I don't know what.
Okay.
Maybe it's a local. It might be a local problem.
Click on the right corner on the button called View, and then change the view to and then you might reach this, get the screen of the presentation.
Oh, I think Lek is frozen. Well, why don't you go? Yes, Lek, can we go ahead?
Go ahead. I should go ahead. All right, I'm going to go ahead.
Yes, please do, because
Okay. All right. So we have tangent vector fields on sphere. So what does this mean? So we let Sn-1, we let this be the unit sphere of Rn. So this is completely the usual thing. That is Sn-1. This is n tuples of real numbers. The sum of the squares is 1. So this is the usual unit sphere in Rn. So a continuous tangent vector field, V, on this n-1 sphere, if you wish, you can look at this as a continuous function from the sphere, Sn-1 to Rn, such that for every point P in Sn-1, V of P is perpendicular to P, where we are using the usual standard inner product. Everything is standard. Everything is as usual. So V of P should be perpendicular to P. Of course, this is using the well-known idea that on the sphere, a tangent vector, it means you have a vector which is perpendicular to the radius vector at that point. So you can look at it this way, that that we are talking about functions, continuous functions, V, from the n-1 sphere to Rn, such that V of P is perpendicular to P for all P in Sn. Now, we then make a definition. We say that continuous tangent vector fields, V1, V2 up to Vr on S-1 are linearly independent if for every point P in the n-1 sphere, V1 of P, V2 of P, Vr of P are linearly independent in Rn. So this is the strongest possible definition of linear independence. If linear independence fails at even just one point in the sphere, then they are not linearly independent. To be linearly independent, you must have linear independence throughout the whole sphere. The strongest possible definition of linear independence. So there is a very natural problem. Oh, this is just saying we are doing all the usual things. Usual inner product, all the usual standard things here. So there was then here's a problem. So let's say we fix some positive integer n. This is, I think, I hope, and I think you would agree that this is a very natural problem. We fix some positive integer n, and then we ask, and we take the n-1 sphere, and we ask, what is the maximum R such that Sn-1 admits R linearly independent continuous tangent vector fields? Now, for example, let's say we look at the even spheres, S2, S4, S6, S8. For the even spheres, the answer is that R is equal to 0. That is it. It does not even admit even 1, because the point is that on an even sphere, on an even dimensional sphere, if you have a continuous tangent vector field, at least one point P in the sphere, V of P equals 0. Well, this is known as you cannot comb the hair on a billiard ball and so on. I mean, this goes back to classical results, like Borsam Ulam. In that time frame, you have this result, that on an even dimensional sphere, the answer to the problem is 0, because any continuous tangent vector field on an even dimensional sphere has at least one 0. And so the answer to this problem on an even sphere is, even dimensional sphere, is 0. The answer is 0. Well, here is the theorem of Adams. So we are on the n-1 sphere. We take n, and we write n in this way. We write n as a power of 2, where the exponent here will be either 0, 1, 2, 3. In other words, this power of 2 here will be either 1, 2, 4, or 8. So we have a power of 2, which is 1, 2, 4, or 8. Then we have some power of 16, and then we have an odd integer. So we write n in this way. We define rho of n. We take this power of 2 that we had. Then we take the exponent on the 16, we multiply it by 8, and we add that. We call this rho of n. Then Sn-1 does admit rho of n-1 linearly independent continuous tangent vector field. This is actually this is not very difficult, because this can be done by studying Clifford algebras, and you see that it does admit these n-1. This is known as the Hurwitz-Redan number, and you can, using Clifford algebras, you can construct these vector fields. So it does admit rho of n-1. And now comes the hard part. And Sn-1 does not admit rho of n, linearly independent continuous tangent vector. In other words, the answer to the problem is this number rho of n-1. And this, Adams's paper about this was published in the Annals of Mathematics, 1962. It uses K-theory. And as far as I know, this is the only solution we have to this problem, is the solution that Adams gave. It seems to depend on K-theory in a very essential way. Adams had been getting partial results using ordinary cohomology. He started introducing cohomology operations and secondary operations, tertiary operations, higher and higher order operations, getting more and more complicated. I like to say that it was a little bit like what was going on with the planets, the cycles, epicycles, epicycles. This is if you take the Earth as the center. Things get more and more and more complicated. But then the great thinker, Copernicus, he said, no, let's take the sun as the center, and so everything becomes much simpler. So Adams said, no, let's take K-theory, not ordinary cohomology, but K-theory, and everything becomes much simpler. And in a remarkable work, he solved the problem.
Sorry, may I ask a question?
Sure, please.
So in particular, this theorem specifies to the even dimensional spheres, yes? And in this case, Cn
Oh, yeah,
and Dn are just 0, yes?
Yes, this is a well taken point. If you have an even dimensional sphere, so then and you work this out, you will get that rho of n is equal to 1, and so then rho of n minus rho of n will be equal to 1. So rho of n minus 1 is 0. Yes, and rho of n will be 1. And you see, for an even dimensional sphere, I was using n minus 1 for the dimension of the sphere. So if this is even, then this n here is odd, correct?
Mhm.
See,
Yes,
if
exactly.
the dimension of the sphere is even, then n is odd. That means that this number will be 1 and this number will be 1. In other words, this exponent will be 0 and this exponent will be 0. So rho of n then will be 1. Yeah. This number is 1. This number is also 1, and this number is 1. So this exponent is 0. So this number becomes 0, and this number is 1. So rho of n is 1. So if n minus 1 is even,
it's okay. It's okay.
yeah, it's okay. Okay. All right, good. Anybody else? Anybody? Yeah, so it works out perfectly for even dimensional spheres. Anybody else?
So in particular, the point is that there are not so many linearly independent continuous tangent vector fields, yes? Since n is of the form 16 to the power dn, and rho uses dn. So this is somehow some kind of logarithm, yes, of this exponent of this number.
No, this is a very well taken point. There's a kind of periodicity involved here. This is actually related to some extent to Bott periodicity. All of this is explored in a well-known paper, Atiyah Bott Shapiro, about Clifford algebras. Yes, there's a well taken point here. There's a kind of periodicity to this number. Yes, very good. Right.
Okay, thank you.
Anybody else? Yeah. In other words, you see what I think the point that is being made here is that this number is independent of you. See, it only depends on this part of it. And that gives a kind of periodicity to what's going on here. Yeah, okay. Anybody else before we go on? Okay. So let's see. This is Adams, who won the race and solved the problem. Now, the C-star algebras. So a Banach algebra, this is a Banach space. It has a norm in which it is complete. We are working over the complex numbers. So it's a complete normed algebra. These are the axioms for a Banach algebra. They are on the screen. A complete normed algebra. Okay. This is the main axiom that relates the multiplication in the algebra to the norm. Okay. So that's a Banach algebra. Now, a C-star algebra, this in fact is a Banach algebra, but it has an extra structure, the star, which is its involution. This is a map from A to A. Little a goes to little a star. And these are the axioms for the involution. It's conjugate linear. The involution is conjugate linear. It reverses multiplication, but it preserves addition. You do it twice, you get back where you started. It's an involution. Now, a star homomorphism. This is an algebra homomorphism from A to B, which is consistent with the star in the 2C star algebra. Now, if we have a star homomorphism, it's a lemma that it's norm reducing. So it's continuous in a very strong sense. It's uniformly continuous. It's norm reducing, any star homomorphism. So this is in the category of C star algebras. These are the morphisms, these star homomorphisms. So this is C star algebras. So for example, if we have a Hausdorff locally compact space, we can form the one-point compactification. We add a point at infinity. And then C naught of X, this is all continuous functions, continuous complex valued functions. So continuous functions from the one-point compactification to the complex numbers, which take the value 0 at the point at infinity. And then we let the norm be the sup norm. C star algebra norms are always, in some sense, sup norms. And then the star, the involution, is that you take the conjugate function. The operations are the naive pointwise operations. Alpha plus beta of p is equal to alpha of p plus beta of p. Alpha beta of p is equal to alpha of p times beta of p. And then the scalar, the action of the scalars is the naive one. Lambda alpha applied to p is equal to alpha of p times lambda. Now, if C is compact, if C is not just locally compact, but compact Hausdorff, then the point at infinity is some isolated point off apart from the space. And you can forget about it because we require the functions to take the value 0. So if you have a compact Hausdorff space, then C naught of X is just all continuous functions. From this we already had. It's all continuous functions from X to the complex numbers, if we start with a compact Hausdorff space. Okay. Now, if we have a separable Hilbert space, separable means that the Hilbert space admits a countable or perhaps finite orthonormal basis. If we look at all the bounded operators, what does that mean, a bounded operator? Well, it's in the sense of linear algebra, it's a linear transformation, a linear map in the sense of linear algebra. But this number, this sup, you take sup over the unit sphere of the Hilbert space. You take sup over the unit sphere of the Hilbert space norm of TU. That must be finite. And that's what we mean by a bounded operator. If this number, the domain of the operator is all of the Hilbert space, and this number, this sup over the unit sphere of the norm of TU has to be finite. This is now a bounded operator. And then the star, these will be a C star algebra. The star is the adjoint operator, which is determined by this equation. Any bounded operator has an adjoint, which is determined by this equation. And then the operations are the usual operations of linear algebra. T plus S applied to some point U in the Hilbert space is TU plus SU. TS applied to a point U in the Hilbert space is T of SU. And then the action of the scalars, which is the complex numbers, lambda T applied to a vector U is lambda times TU. So you take all the bounded operators on the Hilbert space with this norm and with this star, and that's a C star algebra. This is a very important C star algebra. Now, if we have a topological group, which is locally compact and Hausdorff, and second countable. Second countable means the topology of G has a countable base. So what are examples? Well, we have the usual Lie groups. Lie group, I would like to have the convention that it has only a finite number of connected components. So we have the usual Lie groups like SL and R. Then we have for each prime p, there's a completion of the rational numbers called the p-adic field, p-adic numbers or the p-adic field. So that's a locally compact field, and we can work with that. Or we can form Adels that combines the first two examples. This is a ring with unit, the Adels. Or we could make discrete groups like SL and Z. So we have discrete groups are locally compact. Okay, so these are such topological groups, locally compact, second countable. And now, for such a topological group, we have the Haar measure. So we fix a left invariant Haar measure, and we can then form a Hilbert space, the square summable functions, the functions such that when you integrate the square, you get a finite number. All right. The square summable functions, once we fix, let's say, a left invariant Haar measure, and then we have a Hilbert space, L2G. Okay. So we can form the C-star algebra of all the bounded operators on this Hilbert. Once we fix a Haar measure, we can form the C-star algebra of all the bounded operators on L2G. Now, suppose we take continuous complex valued functions on G with compact support. This is an algebra. Namely, the action of the scalars and the addition are naive pointwise. But what's interesting in this algebra is the multiplication, which is convolution. That's given by this. This is using the group structure. You define this to be the multiplication in this algebra. Multiplication is convolution given by this formula. If it's a discrete group, this is the purely algebraic group algebra, if we are talking about a discrete group. Now, we now have an injection of algebras from the continuous function with compact support to all the bounded operators. Namely, given a continuous function with compact support, we map it to the operator T sub F, where T sub F of U is the convolution of F with U, given by this convolution formula. This is an injection of algebras from the continuous functions with compact support into all the bounded operators on L2G. And then we close this in the operator norm, and that's the reduced C-star algebra. This is what we mean by the reduced C-star algebra. It is a sub C-star algebra of all the bounded operators on L2G, once we fix a Haar measure.
Oh, is it obvious that this is an injection?
No, I think that is not completely obvious, but that's can be proved actually fairly easily. I don't think it's completely obvious, but
okay.
it can be proved. The proof is straightforward. Okay. Any other question about this? So this is called the reduced C-star algebra. This is the most naive and simple-minded way to complete this incomplete algebra to a C-star algebra. So this is the most sort of naive, most sort of concrete and naive way to complete this incomplete algebra to be a C-star algebra, to obtain a C-star algebra. Okay, now, so when we have a C-star algebra or a Bonic algebra with unit, we define abelian groups K1A, K2A, K3A as follows. We take GLNA, this is a topological group, the invertible n by n matrices. The reason it's a topological group is that the norm, the original norm, topologizes the n by n matrices. A sequence of n by n matrices is convergent if you fix any ij, you have convergence in the ij spot. So the norm, the original given norm of the C-star algebra or the Banach algebra, topologizes it's a topological group. And now GLNA embeds in GLN plus 1a. You take an invertible matrix and you put zeros, and then the unit. That's an embedding of topological groups. And then we take the limit. In other words, we take the union. Using these inclusions, we take the union of these GLNAs. Well, and we topologize that. We give it what's called the direct limit topology. So all of this is very standard and straightforward. So we give it the direct limit topology. This is the topology in which a set U included in this GLA is the limit as n goes to infinity. This is defined to be open if and only if U intersect GLNA is open in each GLNA. This is the so-called direct limit topology. That's how we topologize this group. So now when we have a C-star algebra, or it could be a Banach algebra with unit, we define these so-called higher K-theory groups. Here is the definition. For the jth K-theory group, you take the J-1 homotopy group of GLA. So it was important that we topologize GLA so that we can take its homotopy groups. And then we have the miracle of Bott periodicity, which says that if you take the loop space on GLA, and then you take the loop space on that, so you take loop space twice, that's homotopy equivalent in a canonical way to GLA. This means that these higher K-theory groups repeat. That is, Kj of A will be isomorphic to Kj plus 2 of A, when J is equal 0, 1, 2. Now, K0A we have already defined. You work with the idempotent matrices. And so because of Bott periodicity, we have really only two groups, the even group and the odd group. Now, if we have a C-star algebra or a Banach algebra with unit, then the zero group is what we did before. That is, you work with the idempotent matrices, you make an abelian semigroup, and then you produce from the abelian semigroup by a little trick an abelian group. In other words, for K0A, you forget the norm and the star. You just view A as a ring with unit. So I was once giving a talk about this, and I said for K0A, you forget the norm and the star. So one of the mathematicians in the audience, an expert on C-star algebras, was asleep. He was having a nap. And when I said, for K0A, you forget the norm and the star, he suddenly woke up and he said, that is immoral. You cannot do that. However, whether it's immoral or not, you do it. And that's K0A. But for K1A, then you cannot forget. For K1A and all the higher ones, you have to use the norm and the star. It's I think an interesting point that for K0A, you can forget about the norm and the star. Any question about this? So this is the K theory, including higher K theory and Bott periodicity for Banach algebras and C-star algebras with unit. And this slide is describing the Bott periodicity isomorphism of K theory. So what I'm trying to do here is explain to you how simple this is. So K0 of A, this means you work with the idempotent matrices and you make an abelian group. How does that map to K2 of A? Well, K2 of A by definition is pi1, the fundamental group of GLA. Of course, for the base point, we take the unit element in this topological group. Now, so this map, the Bott periodicity map, it assigns, given an idempotent matrix, you make this loop of n by n invertible matrix. The identity matrix, and here you just put e to the 2 pi I t minus 1 times alpha. So this is the Bott periodicity isomorphism. Any question about this? Now, suppose we have a C-star algebra or a Banach algebra without unit, because this will often happen. In many, many examples, there will not be a unit. So what you do is you adjoin a unit. That is, you make a slightly larger C-star algebra, A tilde, in which the original one is an ideal, a two-sided closed ideal, and the quotient is the complex numbers. And then you define KJA is equal to KJ of A tilde. That's for J odd, J1, 2, 3. And then KJA is the kernel, that is the null space of the map from KJA tilde to KJ of the complex numbers. That's for even, for J equals 0, 2, 4. So this is how you extend the theory to Banach algebras or C-star algebras that might not have a unit. And you still have Bott periodicity. You still have Bott periodicity. Now this is functorial. This assignment of these higher K-theory groups to a C-star algebra or a Banach algebra, this is a functorial construction. If you have a star homomorphism from one C-star algebra to another, you get a map of abelian groups. And this has been applied to classification problems for C-star algebras. George Eliot and many other mathematicians have used this because this gives you an invariant. In the work of Eliot, you have to enrich the invariant a bit, but this gives you an invariant that can be used for classification. And you have a 6-term exact sequence. If you have a short exact sequence of C-star algebras, you get a 6-term exact sequence. We are using Bott periodicity here of abelian groups. That's the 6-term exact sequence. Now, the question that Alain and I asked, here's the question. So we start with a topological group. It might be a discrete group. It might be a Lie group. It might be a Piaget group. It might be a Della group. We start with some locally compact Hausdorff and second countable topological group. So these are objects studied in mathematics, these groups. It's a very natural question. What we form the reduced C-star algebra. What is the K-theory of the reduced C-star algebra? It's clearly some invariant of the group, but what invariant of the group is it? This is the question that Alain and I asked. And then we proposed an answer. We introduced a space, E bar G. This is the universal example for proper actions of the group G. And our proposed answer is that you take the equivariant K homology in the sense of Kasparov with G compact supports of this space E bar G. Well, this might not seem like much of an answer to you. I apologize, of course, if this does not seem like much of an answer to you. However, in a certain sense, it is an answer to this issue. Now, if G is compact or abelian, the conjecture is true.
Paul, may I ask you to explain what a proper action is? Because this everybody can get, and I think this is important.
Well, I have a question. Well, I haven't got what is K sub J super G. I mean, I understand the right-hand side is K classes, let's say, and what is on the left?
All right, I will try to explain that.
Intuitively, okay.
In ordinary algebraic topology that we learn in graduate school, if you have some topological space, it has homology and cohomology, right? It has homology and cohomology, and these are dual theories of each other. One is the dual of the other. It's a principle in algebraic topology. I mean, it's a theorem that if you have a homology theory or a cohomology theory, there will always be a companion dual theory. Now this, first, to explain the conjecture, first we have, as Piotr said, we have to talk about proper action, what it means for G to act properly on a topological space. And then we have this universal example for proper actions. And then this is the dual theory of K theory, that is K homology, but taken in an equivariant sense, but also taken, you have to pay some attention to the issue of supports. You take it with G compact supports. Now, what was the question? Oh, the question was to explain this. So this is the dual theory of K theory, that is K homology instead of K theory, but taken in an equivariant sense. But also you have to specify what the supports are of this universal example for proper actions. Now, a proper action, this is an action which, locally speaking, is induced from an action of a compact subgroup. What this means is that all the isotropy groups of points, if you take a point and take the subgroup that fixes that point, that's compact. That you take the so-called isotropy group of the point, or the stabilizer group of the point. For any point, the stabilizer group of that point must be compact. That's one condition for a proper action. The second condition is that the quotient space is reasonable. We are talking about locally compact Hausdorff spaces. The quotient space with the quotient topology is again locally compact Hausdorff. This is what we mean by a proper action. Now, all right, so it's two conditions. The stabilizer group of any point is required to be compact, and the quotient space with the quotient topology is required to be compact Hausdorff. We start with a compact Hausdorff space. A typical example of an action which is not proper is you take the integers z acting on the unit circle by an irrational rotation. That is not a proper action. The stabilizer group of any point is trivial, is the trivial one element group, that's fine. But the quotient space with the quotient topology very definitely is not Hausdorff. It's not a locally compact Hausdorff space. Now, the point is this. We can work with this. This in and of itself, this cannot be studied by using the classical tools of algebraic topology, but this can. This makes a lot of sense to people, to algebraic topology people. This thing can be studied. In particular, we get a beautiful Chern character here, which we don't have present here. And the whole cyclic theory, this whole beautiful theory of Alencon cyclic cohomology, this to some extent, not 100%, but to an important extent, does introduce the Chern character on this side. But here we always have a beautiful, interesting Chern character. Well, I've tried to explain that. If you want me to explain it in more detail, that I understand I've not explained it in very much detail. If you want me to explain this in more detail, that will have to be another talk. Because
No, it's fine. I'm very satisfied.
Oh, wonderful. Oh, great. Oh, all right, good. Okay. Anybody else?
Yeah, there's a question on chat.
What is the question?
Yeah, I'll read it.
It's on chat.
Yeah. So what is the space or maybe spectrum of E bar G here?
Well, E bar G is a very much a classical space. For example, there is one way to say what E bar G is, which is very quick and simple. You take all the probability measures on G, you take all the compactly supported probability measures on G, and you topologize that in a suitable way. That's then E bar G, and the action of G on E bar G is by translation. This is one way to explain E bar G. I mean, that's sort of a quick way that gets it done quickly and immediately. What you might call the truth. What I like to say is the truth is this. You've really been doing E bar G your whole life, first of all. Yeah. You've been doing E bar G all your life because for a Lie group, pi naught G finite, E bar G is what's called the symmetric space. That is, you take a maximal compact subgroup and you divide G by the maximal compact subgroup. That's called the symmetric space. That's E bar G. For a p-adic group, it's the building. It's the famous affine Bruatitz building. For adelic groups, it's gotten by combining the first two examples, the building with the symmetric space. For discrete groups, well, that's probably best to think of it as the probability measures. In other words, it's a finite formal sum of elements in the discrete group with non-negative real numbers as coefficients, but the coefficients add up to 1. So it's sort of the convex hull of the discrete group. Okay, but the quick way to do it is the way I was trying to say. You take all the compactly supported probability measures on G, and you topologize that, and then G acts by translation, by the translation action of a probability measure. So that's one way to. That's one way to explain.
And then you prove that it enjoys the universal property.
Yes. Yes. Well taken point. The universal property is that if you have some proper action, of G on some locally compact Hausdorff space, there will be an equivariant map from G, from the space on which G is acting properly to the universal example, and that map is unique up to homotopy through G equivariant maps. That's why it's called the universal example, for that reason.
Well, let me try to write it.
Oh, you're going to write it, Peter?
Yeah. So you have a space X with some proper action.
Yeah, with some given proper action.
And then it means that there exists a unique map from X into E bar G that is, of course, continuous and G equivariant.
Well, it's unique up to
homotopy.
Up to homotopy. Up to homotopy. It's unique up to homotopy through G equivariant maps.
Yes. Yes.
Hi, Sarah.
Yeah.
What?
Okay.
I can't talk now. I'm giving a lecture in Poland.
Oh, okay. All right. No,
I'll call you back. Yeah.
All right. Sounds good. Sorry about that.
I'm giving a lecture in Poland. I'm in Poland virtually.
What?
I am virtually in Poland. But,
okay. Well, enjoy virtual Poland.
Yeah, I'm at a place called Ben Levo in Poland. I will call you back. Okay.
All right.
Bye.
Sounds
Yeah.
good.
Bye.
All right.
Bye. Bye. Okay. Now, this map is unique up to homotopy through
Yes.
covariant maps.
Yeah.
Excuse me, Paul, can I have a question? So this model with measures, does this work for only for discrete groups or for all locally compact Hausdorff groups?
That works for all of the groups. That
Okay.
model works for all of the groups. Yes.
Okay, thank you.
In fact, if you play around a little, Scandalese and some Scandalese, there's a paper by Scandalese, I forget Scandalese and another one of the French mathematicians. If you play around a little bit with that model, so you don't take probability measures, but you take measures where the total mass of the group, there's some definite limits on the total mass of the group. You use that as your model. You actually get a locally compact space for E bar G.
Mm-hmm.
But the idea with the probability measures, that works for any locally compact group. That work, not just discrete groups, but for all locally compact groups. Anybody else? But I mean, the point I'm attempting to make here is the probability measure idea. I mean, that does it, that gets it done. But I think it's better to go back, I tried to list the examples. What are the examples? The examples are, here, With these examples, in each case, except for discrete groups, here it's the symmetric space. That is, you take your Lie group and you divide by a maximal compact subgroup. That's called the symmetric space. Here it's the building, the famous affine Buratitz building. And here you combine the first two examples and you get a very natural space on which the Adelic group acts. Here, well, if it's a discrete subgroup of a Lie group, like this is, then you take it to be the symmetric space of the Lie group. So for a compact group, it's a point. You can take it to be a point. Because for a compact group, the action of a compact group on a point is proper. But if the group is not compact, the action on a point is not proper. So for a compact group, you can take this E bar G to be a point. So in topology, where you have EG, for a compact group, this is already a very interesting and subtle space. So I was trying to convince a topologist that this E bar G was interesting. And I said, look, for a compact group, it's just a point. Look how simple it is. This is what I said to the topologist. Well, the topologist was not buying. And he said, well, I think it's too simple. So you are in some sense measuring the fact that the group is not compact. So see, this comes through here with the Lie groups. A Lie group has a maximal compact subgroup. You divide out by that. That's called the symmetric space, and that's the E bar G. Okay, any more questions about E bar G? Here, I'll go back where we were. So where were, all right, so any further questions about G and E bar G? All right, if G is compact or abelian, the conjecture is true. So most of the interest is in groups which are not compact and not abelian. Now, there are many corollaries of if the conjecture is true. For these corollaries have to do with the conjecture being true for one particular group. We're not saying the conjecture has to be true in total generality. But if for one particular group, we have proved that the conjecture is true for one group, then all these different conjectures, these are all famous conjectures, all of them are implied. All of them are corollaries. What is the idempotent conjecture? The idempotent conjecture, or let's say the Kadison-Kaplansky conjecture. What is the Kadison-Kaplansky? Kadison-Kaplansky says that if you have a discrete group, countable, let's say countable discrete group, you form the C-star algebra, the reduced C-star algebra. Of this discrete group. So the Kadison-Kaplansky says that if the discrete group is torsion free, then there are no idempotent elements in the reduced C-star algebra except for 0 on 1. I mean, 0 on 1, 1 is the unit of the reduced C-star algebra. So Kadison-Kaplansky says that if you have a torsion-free discrete group, you form its reduced C-star algebra, there are no idempotent elements other than the totally obvious one, 0 on 1. And then there are all these other. This is an interesting one, is the construction of the discrete series. This plays an important role in representation theory of semi-simple Lie groups via Dirac induction. And so if the conjecture is true for one particular group, then all these other things are true. Of course, that has two sides to it. I mean, on the one hand, that creates interest in the conjecture of Alain Kahn and me. But on the other hand, if you make a conjecture which implies everybody else's conjecture, your conjecture might not be true. I mean, might not be true in complete generality. Okay.
Or at least it's very difficult to prove.
Yes, or at a minimum would be extremely difficult. All right, now let's look at our examples. For Lie groups, Lie group, I mean with a finite number of connected components. For Lie groups, the conjecture is true. It's known to be true. This is due to Vincent-Lefort. For p-adic groups, the conjecture is true. It's known to be true. What are called reductive, p-adic reductive groups. This is due to Vincent-Lefort. For adelic groups, in a suitable way, you combine the first two. This was done by, it's a matter of, in the right way, combining the first two cases. This was done by Roger Plyman and his student, Roger Plyman, and also his student, and also me. I also worked on this. Okay. For discrete groups, we have many examples where we don't know whether the conjecture is true or not. This is Roger Plyman, who worked on the p-adic group case and the adelic group case and got very good results. This is Nigel Hickson, who got very good results, who I'll try to explain in a moment. Yeah, this is Hickson and Kasparov, Gennady Kasparov. If you have a discrete, let's say, countable group, which is amenable or AT-amenable, this is a big weakening of amenable. This is a major weakening of amenable. Then the conjecture is true. And then we have Lefort, once again Lefort, but also Golyan Yu and Igor Mineyev.
Well, excuse me, when was it done? I mean, which year? The previous one and this theorem?
This one?
Yes, more or less when?
I think this was done around, I'm not completely sure, but I think it was done around maybe 20 years ago, around 2000, somewhere around 2000. Does anybody know when it was? Around 2000. This is a paper by Nigel Hickson and Gennady Kasparov. Somewhere around 2000. Here we have Belian, you and his co-worker Igor Menev, and also Vincent. So Vincent Lefort has contributed quite a lot to this whole discussion. Quite a lot. For SL3Z, we do not know if the conjecture is true or false. We know injectivity of the map. We know injectivity for discrete subgroups of Lie groups. But we don't know if the map is surjective. So as a result of that, because we don't know, I think that Kasan-Kaplansky is unknown for this group. However, this is not a torsion-free group. No, anyway, a suitable generalization of Kasan-Kaplansky. If you take, this group has torsion-free subgroups of finite index. So those are torsion-free groups, and we don't know Kasan-Kaplansky for those groups. So I think this is the main question about the conjecture of Alenkon. Is it true for this group? Now, this is a property T group, but we have many, many examples of property T groups where the conjecture is known to be true. These groups, these hyperbolic groups, in many cases, are property T groups. So property T is not the outer boundary of the conjecture.
Well, just a quick question, if I may. You mentioned SL3Z. How about some higher ends, SL4, SL5, SL million?
Oh, it's not known.
It's not known. Okay.
For SL2,
it's known.
It's known. For SL2, the conjecture is known to be true. But for SLNZ, with n equal to or bigger than 3, we don't know.
Okay, thank you.
I mean, there's nothing wrong with this group. This is a perfectly good group.
Mm-hmm.
It's property T group, all right, but many groups are property T. Property T was introduced by Kajdan, but as I was trying to say earlier, that these groups here, many of these hyperbolic groups are property T groups. Now, these are groups which in some sense are negatively curved, these hyperbolic groups. That is, if you form the Cayley graph of a group like this, it has negative curvature. Whereas these groups are at the opposite extreme. These are groups which in some sense are flat or positively curved. So at the two extremes of the theory of discrete groups, these amenable or AT-amenable groups, at the two extremes of the theory of discrete groups, we know the conjecture is true. So the outer boundary of the conjecture definitely is not property T. However, I should say, Lefort has introduced a strengthened form of a strong property T, and it is possible that the conjecture might fail for these strong property T groups. That's quite possible. You know who this is? Who is this?
Raoul Bott.
This is Raoul Bott. He was wonderful. I was a little bit friendly with Bott, and we wrote a couple of papers together. He was absolutely wonderful. There he is. Oh, you know who this is?
Yesterday's speaker.
Right. This is Alenkon. Oh, in the background. What is the background?
Oberwolfach.
Right. It's Oberwolfach. This was at a meeting in Oberwolfach. Oh.
That's the conjecture.
This is at that same meeting in Oberwolfach. On the right of the screen is Alenkon. On the left is a suspicious character. Okay, now I want to say something about algebraic K-theory. Suppose we have a group just a discrete group. Let's say we have a discrete group. Not topologized. The group is not topologized. It's a discrete group. There's then a space called its classifying space, denoted by B gamma. This is a triangulable topological space, or if you like, it's a CW complex, if you prefer that. It's connected. Its fundamental group is the given discrete group gamma, and its higher homotopy groups are 0. So if you take a free group on 2 generators, the classifying space for the free group on 2 generators, you take 2 circles and join them at a point. You see pi 1 of this, you have 2 loops. You have a loop here and a loop here. They generate the fundamental group. There are no 2 cells here to give relations, so you have a free group on 2 generators. This is the classifying space for a free group on 2 generators. All the higher homotopy groups are 0 because the universal covering space of this is a tree, right? It's a Baum, it's a tree. I guess in this case, it's the 4 regular tree, right? It's the tree with exactly 4 edges at each vertex. But the homotopy groups of a tree are 0. So all the higher, so anyway, this is the classifying space of the free group on 2 generators. On the other hand, if we have the 2-element group, its classifying space is RP infinity. You take RPn and you include it in RPn plus 1. This is real projective space. And then you take the union, the direct union. That gives you the classifying space for the group with two elements. So this is the classifying space. Now, algebraic K theory. Excuse me a moment. Hello? I can't talk. Hello. All right. All right. So we have a ring with unit, let's say. We have defined the 0th K theory. We work with the idempotent. This never changes. This is always the same. So you do what we did with the idempotent. Then we take the limit of the GLNs of the invertible matrix. We take the union, so n goes to infinity. But it's not topologized. See, if we had a Banach algebra or a C-star algebra, there'd be a topology here. But here, there's no topology. All right, now the K1 algebraic group is you abelianize GL lambda. That is, you take GL lambda. It's not topologized. It's just a discrete group. And you divide out by the commutator subgroup. This is then perfect. That means that is the commutator subgroup is perfect. That means the commutator subgroup is equal to its own commutator subgroup. That's called perfect. This allows you to do what's called equivalent plus construction, this lemma. So you take this B, the classifying space of GL lambda, but then you do the equivalent plus construction on that. The original B maps to the equivalent plus construction. Pi 1 is isomorphic. It's just the abelianization of GL lambda. And in homology, this is an isomorphism. This characterizes the equivalent plus construction. And then you define the higher algebraic K theory groups to be the homotopy groups of this BGL lambda plus meaning you have done the equivalent plus construction. You then extend to the case when lambda does not have a unit. You adjoin a unit, but now the quotient ring will now be Z. And you extend. Then you have some very interesting conjectures due to Steve Lichtenbaum. If you have a totally real algebraic number field, then for n equal 2, 4, 6, if you take the zeta function of the field, you evaluate on n minus 1, you have the ring of what's called the ring of integers in the number field. You take the these are algebraic K-theory groups. They are finite. You divide by the order of these finite groups, and then you have a plus minus, and then up to powers of 2. This is Lichtenbaum, Steve Lichtenbaum, very nice guy. And then you can generalize this. It doesn't have to be totally real, but it introduces a new idea, which is called the Borel regulator. And so it generalizes. So this has a completely different feel. This is Quillen, Daniel Quillen. All of this has a completely different feel from what's going on with Banach algebras and C-star. It's much more algebraic. It has to do with algebra and rings of integers and so on. Now, in the K-theory of C-star algebras, there's a trivial move, which is called stabilizing the algebra. You form the n by n matrices. It's again a C-star algebra. The star is, you flip the matrix and star all the entries. But you can embed here by putting zeros. That's a one-to-one star homomorphism, and it's norm preserving. And then you take the limit. The limit is these infinite matrices where almost all the entries are 0. But that limit has a norm and a star. And therefore you complete this limit using the norm and the star, and you have a C-star algebra, which is called the stabilization of A. This is the tensor product of A with the compact operators. That's how it's often said. So we denote this stabilization of A by A with a dot over it. A with a dot over the A. Now, Karoubi conjecture.
Paul, could we go back for a second to this Quillen's plus construction, because there's a question in the chat. What is really being done in the Quillen plus construction? Can you do something like that as well if you wouldn't have started with unitaries instead of GL in the C-star case?
This very likely in the C-star case, in the C-star case, well, I'm going to answer what happens in the C-star case. Wait, you have to give me a moment here.
Okay.
In the C-star case, it looks very different. But Karoubi made a remarkable conjecture, which I'm just about to put up on the screen. Yeah, it looks very different, but maybe not. See? So Max Karoubi, okay. This question has an extremely interesting answer. Max Karoubi conjectured that if you take a C-star algebra and you stabilize it, you can then take its K-theory in the sense of C-star algebras. It's the same. It's the same as the original K-theory of the original C-star algebra. Stabilizing the C-star algebra is a trivial move within C-star algebra K-theory. And here's the answer to the question. Karoubi conjectured that if you stabilize the C-star algebra, you could stabilize and not forget that it's a C-star algebra, and you get the same K-theory as the original K-theory. Or you could stabilize it as a C-star algebra, you stabilize it, and then you forget, you just look at it as a ring, and you take the algebraic K-theory. Karoubi conjectured, this is the answer to the question, that you get the same thing. This was Karoubi's conjecture. I told this conjecture to Mariusz Wojcicki, and he immediately, as soon as I told him the conjecture, he started screaming that he would prove it. It took 10 years. Eventually, he brought in André Suslin, and they proved it. They proved the Karoubi conjecture. So, so this is the proof.
One question about this. So really, my question was more, so if you're doing the C-star case, you probably want to consider unitaries instead of GL, right? And
Well,
here, in that case, wouldn't that slightly be different because you have problems about taking the commutators? It's not like when you do, say, K1, you can take GL, you can take U. It doesn't really matter because you have a.
Yeah, I agree with you. There would be a problem. Yeah.
But here there would be a problem, and then my question really was: so this plus construction, that's about topological spaces, right, or about classifying spaces, or was that something specific about taking the classifying space of GL?
There is something very special, which is that lemma about the commutator subgroup being perfect. That's what allows you to do the Quillen plus construction. It can be done on any topological space where the commutator subgroup of the fundamental group is perfect. That is equal to its own commutator subgroup.
All right, thank you.
Yeah, I mean, roughly speaking, the way the conjecture works is that you take the topologist BG, but then in the right way you add cells, you add in cells, you attach in cells to get the kind of relations that you want. That's how the Quillen construction works. But there's a whole literature about this Quillen construction and different ways of thinking of it. So one way of thinking of it is that you take the topologist space, you de-loop it, and then you loop that. That's another way of thinking about it. So there are many different ways, but the way Quillen originally thought about it is you take the topologist BG and you add cells in the right kind of way to it. You attach in cells in the right way to get it to do what you want it to do. So, all right, so Karoubi conjectured, a remarkable conjecture that, so here it's all within C-star algebra K theory. And here you are just dealing with the original K theory of the original C-star algebra. Here you have stabilized it as a C-star algebra, but then taken its algebraic K theory. And Karoubi conjectured that these are the same. And then this was proved by Suslin and Wojcicki. So this is their theorem, the theorem of Suslin and Wojcicki. So this theorem is the unity of K theory. It says that C-star algebra K, this says you really is one subject. It says that C-star algebra K theory is a pleasant subdiscipline of algebraic K theory in which Bott periodicity is. Bott periodicity is not valid in algebraic K theory. It says that C-star algebra K theory is a pleasant subdiscipline of algebraic K theory in which Bott periodicity is valid, and certain basic examples are easy to calculate. We have basic examples which are easy to calculate in C-star algebra K theory, but the basic examples are extremely difficult to calculate in algebraic K theory. So this is the unity of K theory. In algebraic K theory, we have in C-star algebra K theory, we have Bott periodicity. This is the unity of K theory. I thank you for your attention.
Thank you very much, Paul. Okay, any further questions or comments? No, Adam, no? Yeah, okay. One from the audience, one on the chat. No, on the chat is just thank you.
Yes, but I'm not sure whether I can formulate my question correctly, but the stabilization gives you the same as tensoring with compacts, yes, with compact operators.
Tensoring with compacts in the sense of C-star algebra.
In the sense of C-star algebras, yes. Yes.
You tensor purely algebraically, but then you complete.
Yeah.
Yes, yes, and now the algebra of compact operators is Morita equivalent to a point. Okay.
Yes.
To a point, to C. Okay, to C, which is the algebra of functions on a point, and the tensor product in this Gelfand-Naimark correspondence, it corresponds on the topological side to ordinary Cartesian product. So in some sense, in some non-commutative sense, we are crossing our space by a point. And then suddenly the algebraic K-theory turns out to be the same as the topological K-theory.
Right.
And this is my picture in my head, but I don't have a question about it. So maybe your perspective on this point of view, is it something deep or it is just a coincidence? I don't know how to formulate my question. Sorry.
Well, in the sense of C-star algebras, this A dot, in the world of C-star algebras, the stabilization of A is Moridi equivalent to A. And so it has the same K theory.
Yes.
Somehow, when you stabilize the algebra, doing this goes back to an earlier question, which was a very good question. Somehow, once you stabilize the C-star algebra, the Quillen plus construction for a stabilized C-star algebra, the Quillen plus construction is somehow the same as the classical topologists BG or EG. The Quillen plus construction in some sense is not doing anything really once you stabilize the algebra. But to build up a conceptual picture, I think that's a very interesting point. I think the question is how to conceptualize this. Why should this be true?
Exactly.
This would be a very good question to ask to Max Karoubi. Why did he think of this? I mean, it is, of course, true for K naught. I mean, for K naught, this is immediate. I mean, for K naught, this is immediate.
Yeah.
And it's somehow a rather subtle point in homotopy theory for that the Quillen plus construction is not really doing anything different from what we are used to doing in C-star algebras once you stabilize the algebra. Now, how you conceptualize that, you might conceptualize that by taking this point of view that the Quillen plus construction is that you de-loop and then you loop. From that point of view, on Quillen plus, that might give some conceptual answer to the question. That's possible.
Okay.
So,
okay. Thank you.
But Paul, would you agree with the statement that what this Suslin-Wojcicki theorem, which was Karoubi's conjecture, what it tells us that for C-star algebras, the algebraic K theory, what it tells us about sort of the unstable aspect of C-star algebra, the unstable part. Once you stabilize it, it's just the usual K theory.
Well, I think there's some truth in that. Yes. Yeah, you're right.
Yeah,
yeah.
That's what it tells. So it's richer. I mean, even for C-star algebras, the algebraic K theory gives you some more information. Yeah.
Well, suppose we take. Yeah, I want to try to illustrate what Piotr is saying.
Yeah.
Suppose we take as our algebra, we take the simplest possible C-star algebra, namely the complex numbers. Mm-hmm. The norm is the absolute value, and the star is the conjugate of a complex number. Now, the K theory, in the sense of C-star algebras, the K theory of the complex numbers, for K0 you get Z, and for K1 you get 0. And then it's periodic. It goes Z0, Z0, Z0. I mean, this is Bott periodicity. This is a deep and wonderful fact.
Yes, yes, sure.
Sorry?
Yes, yes, of course.
This is Bott periodicity. This is a deep and wonderful fact. It's Z0, 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 okay? And there is, of course, a great deal, a huge amount of content to this fact. Now, if we take the complex numbers and we don't stabilize, we throw away the norm and the star. We just look at it as a ring. The complex number is a ring. And we take the algebraic K theory of that ring.
It is not known, as far as I know.
It's only partially known. There are many partial results about it. it gets huge very big, very quickly. Very quickly you get abelian groups which are uncountable. It's some horrible, huge thing. However, it's important. It's important to figure it out and to understand it. But then the magic in this result is that when we stabilize, it's all the same. In other words, this is saying that for the compact operators, what does it mean to stabilize? It means we look at the compact operators. A remarkable thing happens. For the complex numbers, the algebraic K-theory, I think it's safe to say that the algebraic theory is very, very difficult to understand. But it's important to understand, and there are many, many partial results for the complex numbers, algebraic K-theory. But if we stabilize, what do we have? We have the compact operators. For the compact operators, the K-theory as a C-star algebra and the algebraic K-theory are the same. It's the same thing. This is the miracle of this theorem.
Yes, I agree completely. It's mind-blowing theorem.
Right. So how to conceptualize this? I guess it says we should think of a point as being the compact operators. We shouldn't think of a point as being the complex numbers. I mean, maybe that's one way you could look.
Yes. I was afraid to say so, but I'm glad that you say so.
Perhaps that's what it says. Maybe. Yeah.
Paul, if you allow me, I'd like to somehow continue your answer to Adam's question very, very quickly. So yes, of course, when you have a C-star algebra and you take tensor product with compact operator, that's exactly the stabilizations we are talking about here. But when you look about the Bott periodicity, this is done, as Paul was explaining, through this double suspension, right? And what really is a suspension? This is a tensor product with functions vanishing at infinity on the real line. So when you do double suspension, and remembering what you yourself said, that the tensor product corresponds via Gelfand-Naimark to the Cartesian square, so this is just tensoring with C0 of R2, okay? And again, this is the invariance of K-theory under this tensor product is Bott periodicity, and this is the Morita invariance. But as many people know, for instance, working in quantum groups, this is just some deformation quantization of the C-star algebra. So somehow, it's probably completely stupid, but somebody could just replace in this Karoubi's conjecture the stabilization by compact operators with this double suspension. Of course, it wouldn't change the K-theory at the level of C-star algebras, but what would it be at the level of algebraic K-theory? But this is just too naive. It surely has no chance of being remotely true. But I at least wanted to point out at this remarkable relevance between the Bott periodicity and Morita invariance, that it somehow comes by a very same process, except you can think about the Morita invariance as a quantum double suspension invariance. Okay. Anybody else? There are some things on chat, but let me see if there is. Wow, wait a second. There's so many. Okay. Thank you. This is okay. Thank you. Is the C-star algebra K-theory what people call topological K-theory, or is it a third thing?
No, the C-star algebra K-theory is what people call the topological theory, because it depends on having a topology. Yeah, that's topological K-theory.
Okay. Oh, yes, yes. Somebody actually answered this question in the chat. Yeah, okay. So any more questions from the Zoom folks? From the audience? I guess not. So let's thank Paul again for this wonderful talk.
Thank you. Thank you.
And oops, we stop recording. And this recording will be available on YouTube sometime tomorrow morning or in the afternoon. So please subscribe to the Banach Center YouTube channel
or look up our conference homepage. Okay, so I stop recording and thank you so much for being here.